Welcome. In this video, we look at Chapter 4, Number Theory, and the section B, Prime Numbers. We'll talk about just prime numbers in general. What are they? Prime factorization, the sieve of Eratosthenes, and then 3 other prime facts. To begin, prime numbers. A natural number greater than 1 is prime, if its only divisors are 1 and itself. A natural number greater than 1 is composite, if it is not prime. So, for example, here are the first few natural numbers greater than 1. And when I look at these numbers, I might start to think about factoring them. How do these numbers factor? Now, the number 12 can be factored into 2 times 6. I have a factorization other than just 1 and 12. On the other hand, 17. How can I factor 17? And the only way that it can factor is as 1 times 17. So since 17 can only be factored this one way, it's prime. But since 12 has a different kind of factorization, it is composite. Here we go. I got rid of all the composite numbers and only the primes remain. So you have a sense of the first few prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23. What about number 1? People often ask this. Is 1 prime or composite? And the answer is, it is neither. When we talk about prime or composite, that description only applies to natural numbers greater than 1. 1 is neither prime nor composite. Here's a list, again, kind of giving you just a bigger visual sense of how prime numbers behave. This is a list of all the primes up to 700. And I've left blanks for the composite numbers, so you can kind of get a sense of how the primes are distributed. And it starts off that there are quite a few primes right away, 2, 3, 5, 7, 11, 13. But maybe one thing you notice is that as we move on and we get down closer to the bottom of the list, the primes become a little more sparse. Up near the top of the list, every row has maybe 5 or 6 primes in it. Down below, it's a little bit less. It's maybe 4 or 5 primes. In fact, I think maybe there's one row that has only oh, look at that. Here's a row that has only 3. I think maybe there's a row that has only 2. There's a lot of randomness to how these primes appear to be distributed. This is one of the great fascinations with primes that people have had for literally millennia. Generally, it appears that as the numbers get larger, there's a little more space between prime numbers, but there's also just a lot of weird randomness going on here. Let's talk about prime factorization. And here's our big idea, the fundamental theorem of arithmetic. This is an ancient result, thousands of years old. It says every composite number can be written as a unique product of primes. So what do I mean by that? Every composite number can be written as a unique product of primes. If I take 360, which is a composite number, I can write it as a product of primes. And I can only write it as a product of primes in one way. Let's see how that works. Let's take 360, and I'll start trying to divide it by numbers as much as I can. It's divisible by 2, so I can write 360 as 2 times 180. 180 is divisible by 2. 2 times 90. 90 is divisible by 2. 2 times 45. And I can use divisibility rules to help me find small factors. Like, is 45 divisible by 2? No, of course not. Is 45 divisible by 3? If you want, you could use the rule of 3. 4 plus 5 is 9. 9 is divisible by 3. Oh, yeah, so it is. So you can divide this by 3, and you get 3 times 15. 15 is divisible by 3. 3 times 5. And at the end, I can't factor 5 anymore. 5 itself is prime. The leaves on this tree, sort of the ending values, those are all prime numbers, and the product of those make 360. So you can see I have 3 2's. If I multiply 2 times 2 times 2, that's 2 cubed. I have 2 3's, so that's 3 squared, and I have a single 5. So 360 can be written as 2 cubed times 3 squared times 5. Let's do another example, 3,850. Can you see divisible by 2? Now 1925 is divisible by 5. 385 is divisible by 5. 77 divisible by 7, so pull a 7 out there. I'm left with 11. And I end up with my primes 2, 5, 5, 7, 11. So the number 3,850 can be written as a product of primes 2 times 5 squared times 7 times 11. So this is the prime factorization of a number. When I can write a number as a product of primes, then that's the prime factorization. Let me talk about this word unique. What does it really mean that this composite number is written as a unique product of primes? So earlier, we found that 360 was 2 cubed times 3 squared times 5. What if I try to break down 360 in a different way? Maybe the first thing you notice is that this is 36 times 10. And then the 36 is 6 times 6. And 10 is 5 times 2. But then each of those 6's is 2 times 3, 2 times 3, 2 times 3. So I might create a different factor tree as it comes down. And at the end, though, I really end up with the same thing. I have 2's. I have 3 2's, so that's 2 cubed. I have 2 3's, so that's 3 squared. And then I have a single 5. So no matter how I break it down, the prime factorization that I end up with at the end will always be the same. The sieve of Eratosthenes. This is a great idea. It was the ancient Greek mathematicians that really did a lot of the early study with prime numbers, and Eratosthenes is one of those ancient Greek mathematicians. In fact, he was a well-known scholar in his day, and he was the first person to come up with a fairly accurate estimate for the circumference of the Earth. And Eratosthenes came up with this process for finding prime numbers. Here's what he said. He said, suppose that I want to find all the primes from 2 to 100. First of all, you just list them all out. List all the numbers from 2 to 100. And now what we'll do is we'll start crossing off the composite numbers. So on this list, you sort of start at the beginning and identify the very first number on that list. It is 2. So 2 is prime. The next thing you do is cross off all multiples of 2. Now, everything I've crossed off has to be composite, right? Because everything that's crossed off has a factor of 2. Things are prime if the only factors are 1 and themselves. So all those numbers I crossed off have a factor of 2. They can't be prime. Cross them off. They are composite. At this point, I look for the next number on my list, the 3. And now I do the same thing. Let's cross off all multiples of 3. 6 was the first multiple that got crossed off. You can see it was already crossed off by 2. And then 9 is the next thing that got crossed off. Oh, and you can see 9 is the first thing that was crossed off that hadn't been crossed off before. All right. And so now we've crossed off all multiples of 2 and 3. Move on. Take the next number that hasn't been crossed off already, 5, and let's cross off all multiples of 5. Now, as I go on here, I see 10, but 10 had been crossed off previously. 15 is removed, but 15 had been crossed off already. 20 is removed, but 20 had been crossed off already. 25, oh, 25. So look at that, 25 is the first thing to be crossed off as a multiple of 5 that hadn't been crossed off before. And 25 is 5 squared. So maybe that kind of makes sense. I mean, 5 times 2 would have been crossed off. 5 times 3 would have been crossed off. 5 times 4 would have been, because it's a multiple of 2. But when I get to 5 squared, that's the first new thing that gets crossed off. In fact, do you remember when we were crossing off multiples of 3, 9 was the first new thing that got crossed off. When I cross off multiples of 5, 25 is the first new thing that gets crossed off. All right, let's continue our process here. I've crossed off all multiples of 5. Let's move on to the next uncrossed off number on our list, 7. And we will cross off all multiples of 7. And what is the first thing that was crossed off that hadn't been crossed off already? Can you see what's the first multiple of 7 that was crossed off that hadn't been crossed off already? And the answer is 49, which is 7 squared. Believe it or not, I'm actually done. I've crossed off all the composite numbers from 2 to 100, and it seems remarkable. I've only crossed off multiples of 4 numbers. How can it be that all the composite numbers have been crossed off? Well, let's imagine that we continued this process. So 7 comes across here, loops around. If I started crossing off multiples of 11, what would happen? Well, 22, well, that's already been crossed off. 33 has been crossed off. 44, 55, 66, 77, 88, 99. In fact, what would be the first multiple of 11 that gets crossed off that hadn't been crossed off before? It would be 11 squared, but 11 squared is 121. It's bigger than 100. So I don't need to cross off multiples of 11. Every multiple of 11 under 100 has already been crossed off. So, at this point, all composite numbers up through 100 have been crossed off. I will remove them. Here we go. Watch this. They are slowly fading away. And the only thing that remains are the prime numbers. And so this was kind of the genius process of Eratosthenes. It requires very little work, and I can get a lot of prime numbers right away without having to do division. Division is tough, but multiplication is easy. And here's the idea that the square root of 100 is 10. So I find the biggest prime under 10, which is 7, and I only have to cross off multiples of primes up to 7. Now, the square root of 1,000, well, that's approximately 31.6. So if I wanted to find all the primes up through 1,000, I'd have to cross off multiples, but how far would I have to go? Well, I'd cross off multiples of 11, 13, 17, 19, 23, 29, 31, and then stop. Once I've crossed off all my multiples of primes up through 31, I know that even if my list is 1,000 long, the only numbers that remain are the prime numbers. Let's talk about some other prime facts. I have 3 prime facts that I will share with you. Number 1, there are infinitely many prime numbers. These prime numbers keep going and going and going. They don't ever stop. This proof was given by another ancient Greek mathematician, Euclid, a little earlier than Eratosthenes, so this was about 300 BC. And Euclid had the idea that given a finite list of primes, he can prove that there exists a prime not on the list. Here's a very short example of the kind of thinking that Euclid did. For example, start with the numbers 2, 3, and 7. 2, 3, and 7 are primes. And then Euclid had this clever idea. He said, consider this number t, where I'm going to multiply those primes and add 1. So in this case, 2 times 3 times 7 plus 1 is 43. We'll analyze it in terms of the 2, 3, and the 7. 2 is not a factor of 43. And we can just see this pretty quickly because 43 is not even. But also, 3 is not a factor of 43. If I try to take 3 into 43, it leaves a remainder of 1. And 7 is not a factor of 43. If I try to take 7 into 43, well, let's see, 7 goes into 42 evenly, but then it leaves a remainder of 1. So in fact, 2 into 43 leaves a remainder of 1. 3 into 43 leaves a remainder of 1. 7 into 43 leaves a remainder of 1. 43 is not divisible by 2, 3, or 7, and it's because of this plus 1. That's what prevents it from being divisible by those numbers. Now that I've got this new number that is not divisible by any of the primes I started with, I can use the fundamental theorem of arithmetic. Either 43 is prime, or 43 has a prime factor other than 2, 3, or 7. But in either case, this proves the fact. This proves that there has to exist some prime number other than 2, 3, and 7. And just for the record, it does turn out that 43 is prime. Here is officially Euclid's proof. There are infinitely many prime numbers. And what I'm about to show really is literally the proof that he gave. I mean, not in English, he gave this proof in Greek, but basically this is what he wrote over 2,000 years ago. List any n primes, so a prime 1, prime 2, prime 3, up through prime n. It doesn't really matter how many primes you list, just list a bunch of primes, but stop at some point. Make a new number, capital T, that is the product of those primes plus 1, and then it has to be that this big number t that I've just created, it's either prime or it's composite. Let's consider the two cases. If that number is prime, then it's a new prime not already listed. If t is composite, then it must have a prime divisor, by the fundamental theorem of arithmetic. However, none of those original primes that we listed, none of those primes actually divides t evenly, because when I try to divide one of those primes into t, it always leaves a remainder of 1. Because of this clever trick, we have that plus 1 in there. Thus, the prime divisors of t are not on the original list. And so, there exists a prime number not on the list. Do you see what happened? He said, give me any finite list of primes, and I will prove to you there exists some new prime not on your list. What do we conclude? There must be infinitely many prime numbers. It's kind of neat to look at this reasoning, look at this logic, and think that we're tracing the same kind of logical deduction that this mathematician over 2,000 years ago went through. Here's our second big prime fact. Generally, primes become sparser as the numbers get larger. There exist arbitrarily large gaps between primes. So here's what I mean by gaps between primes. There's a gap of 3 following prime 7. So 7 is a prime, then I have 8, 9, 10, and 11. 7 is prime, 11 is prime, but the 3 numbers in between are composite. So we might say that there's a gap of 3 following prime 7. So you can see that these gap numbers grow larger and larger and larger. There's a gap of 51. There are 51 consecutive composite numbers following the prime number, 19,609. And it turns out that these gap sizes, they just keep growing and growing and growing. If I go out far enough in the numbers, I can find a gap that's over 1,000 long, 1,000 composite numbers in a row, or 1,000,000, or 1,000,000,000,000. I can find somewhere, if I go out far enough in my numbers, 1,000,000,000,000 consecutive composite numbers. That's kind of interesting. Here's that table that's been extended a little bit. The first time we get a gap of over 1,000, that follows the prime. Oh my gosh, what is that number here? Let me put in some commas and I'll try to read this out loud for you. Here we go. So we have a gap of 1,000 consecutive composite numbers following the prime number, 1,693,182,318,746,371. So you do have to go quite a ways out in these numbers in order for these long gaps to appear. Our third prime fact, there appear to be infinitely many twin prime pairs, but that is an open problem. A twin prime pair, that's when you have 2 primes that are just separated by 1 composite in between, like 11 and 13. So it's kind of like primes that are very close to each other, sort of the opposite of our previous result. Previously, we saw that the gaps between primes get larger and larger. But, there's kind of a lot of randomness between these primes also, and sometimes you find these primes that are just right next to each other. So I'll highlight a few twin prime pairs. I know I'm going to miss a lot. I'm not trying to get them all, but you can see that throughout this array, there are lots of these things, twin prime pairs. And it appears, mathematicians believe, that these twin prime pairs continue forever and ever and ever, that there are infinitely many of these pairs. But, curiosity, this is an open problem. Nobody actually knows. This is a current problem, so there are brilliant mathematicians right now trying to prove this, trying to prove that there are infinitely many of these twin prime pairs. They don't just stop at some point. So who knows? Maybe it could be you. Maybe you will someday prove that there are infinitely many twin prime pairs. All right, and with that, I will stop my introduction to prime numbers.